Okay, so this is an example with a heat equation with so-called inhomogeneous boundary conditions. So that refers to the fact that the boundary conditions over here are not zero. Okay, so let's see how we will attack this and what's different from a standard heat equation. So this is a quite common, quite standard ODE problem. So again, let's identify the four ingredients we have in a PDE problem, in a partial differential equation problem. What is the four ingredients? It will always have the function of interest, the target function, domain of validity, the PDE itself of interest, and the boundary conditions. So we find that, okay, the temperature of a rod is described by this function, u of x and t, so it's multivariable function, and the domains of those parameters are x and t, okay? And we see that this is a semi-infinite domain on t and a finite domain on x and L. Good, okay, so this would be a Sturm-Liouville problem, hopefully. And this is a time-like variable, a space-like variable. The PDE in question, right? So the temperature will satisfy this diffusion equation or heat equation, right? So the temperature is described by U, and U satisfies the rate of change is proportional to the curvature of the profile, the temperature profile. And okay, so that's just a constant, k equals to 4, and we will set the length equals to 1, and these are the boundary conditions. So every PDE problems will have these four ingredients, right? Okay, and as we talked about in class, we might want to start with drawing a domain diagram, domain and boundary condition diagram to translate all these written information in just a diagram. Of course, I distilled this question already into quite just the essence, so it's quite simple, especially clear if I put these in a box, but normally when you get a question, it's a whole paragraph and it's sometimes very convoluted, right? All the information is hidden. It's good to translate it into a diagram. Now, you can almost just cover this up and still completely solve the question with the diagram. Okay, so we have x and t. So t goes from 0 to infinity, and x goes from 0 to L. And we're setting L equals to 1. So the whole domain is within this boundary. So we're trying to solve u within this space over here. What are the boundary conditions? Well, at u, so notice what's going on over here. This is an initial condition on t. So this is when t equals 0, and these are the boundary conditions when x is 0 and the other one is x equals to L, right? These are for all t, well, technically for all t in the domain, whatever the given domain is, and this initial condition works for all x, again, in the domain of interest. So let's start with this, t equals to 0, x equals to 1, okay? All right, so over here, on t equals to 0, over here, let's write this out. 0 is equals to 1, okay? So the whole rod starts off at a uniform temperature at 1. Okay, interesting. So you have a uniform temperature rod lying over here. And then at x equals to 0 over here, we are now, as soon as we evolve time, as soon as time moves on from 0, we make sure u equals to -1 here, right? And then we make sure u equals to 3, okay? So the uniform temperature rod, we immediately on one side cool it down, the other side heat it up, right? Okay, so and the question is to find what is u in the parameter space in the middle, right? So it's in this space. What is u? So this is the whole question. You see, the whole thing is summarized into this. Now, before I go on, let's talk a little bit about the theory first, before I properly solve this, is because this is not a Sturm-Liouville homogeneous Sturm-Liouville boundary condition. So first, let me make sure you understand that homogeneous boundary conditions has nothing to do with homogeneous partial differential equation or the differential equation itself. No relation, okay? It's whether this is 0 or not. So remember the standard regular homogeneous Sturm-Liouville boundary conditions are one condition at A and one condition at B, One of them you want you want them to be at A. It can be on either the derivative or on the value itself, right? Equals to 0. And these can be any constants, alpha, beta, gamma, delta. Okay. Right. So now our A is going to be 0. So we are having one boundary condition at 0, and we are having another boundary condition at L or 1. That's fine. In fact, our boundary conditions is fixing it at 0 and L, okay, and it's just on the value, not the derivative. Okay, so we can set this to 0 for our case. Let's make this a different color for our specific case. So for our specific case, these can be set to 0, right? This is our specific case. And alpha, we can set that to 1, and this we can set that to 1, right? So this is at 0, this is L, okay? So this reproduces these parts. However, you see, this is 0, but what we want is, we want this to be -1, and we want this to be 3, right? That's the boundary condition. So this is what the inhomogeneous part, whereas these are the homogeneous boundary conditions. Okay, so now we see that the problem is this boundary condition does not satisfy, it's not satisfy a regular Sturm-Liouville boundary condition. What do we do? So what we do is a trick, and we, instead of solving for u, we change the variable. So continuing on the theory, we do a change of variable, and we go from solving, instead of solving ux, we go to solve another function. Let's call it theta. Okay, theta is the Greek letter for T. So T for temperature. Seems like a good symbol to use. All right. Yeah. So this is a way to yeah. So we will, since this has inhomogeneous boundary conditions, we want to shift and change the variables to this, something with homogeneous boundary conditions. Okay, so what is the relationship between it, right? So let's find out. And here is the trick, is this. So the idea is to do is to break it down and let u of xt equals to 2 parts. One part, let me call it u steady state of x and t plus theta of x and t. Actually, let's call it u, the fluctuation of x and t. Okay, so what's going on? The steady state actually does not. The steady state is the solution for the temperature when t goes to infinity. Okay, so we want to break this down, because let's think about it, right? So we have a rod. The temperature is originally at 1. Let's plot it like this. So this is the temperature, and x, okay, 0 and L. Okay, so at first, the temperature is like this. This is at t equals to 0. What happens, so this is the solution. This would equal to u when you're equal to the original u. So this is the original, the full u, so the full solution equals to u full at t goes to infinity. Okay, and we want to hold this at -1 and 3, right? So when you give it enough time, then when t goes to infinity, the temperature profile should look like this, right? So this is the initial temperature profile. So u is the temperature at t equals to 0. It's just uniformly at u equals to 1. Now you hold these two ends. After infinite time, this should be the steady state solution. Okay, so this is the steady. So this should be yeah, the steady state. Okay, so the steady state here actually won't depend on t, because it's actually already when time equals to infinity. Okay, so we factor, basically we split out the evolution of u into the part where it's basically the end state, if you want, if you will. This captures the end result, the end state. So that's why it's also called steady state, because now the temperature is steady, it becomes equilibrium. And this is sort of the evolution part. So the evolution part, or sort of the fluctuation on top of the steady state, right? So it should slowly go like this, right? So this part would capture that. And this is what in your notes it's called theta. But yeah, it's basically the fluctuation part. Okay, so if you want to rigorously define it, you can actually you can define it like this. You can say let u steady of x equals to the limit of time goes to infinity for the full u of t, right? So u of xt. So when t goes to infinity, or if you want to abuse the notation a little bit, just write this, or even just write this if you want, right? So we're going to define u steady to be this, okay? And we're going to define theta, and theta of xt is the fluctuation, and we define this as the difference between the complete solution minus u steady, like that. Okay, so this is the rigorous way to define the two new variables, because we introduced two new functions, and this is what we're going to solve for. Okay, okay, so let's see. So how would we actually solve it? Well, what is the steady state? The steady state is we know it's going to be a linear profile. Like after infinite time, the temperature is going to look like this. Okay, so yeah, well, what does that look like? Well, just simple linear equation, linear straight line. So y equals mx plus c, right? Y-intercept is well, what's the gradient here? What's the slope? It's 4, right? If L equals to 1, then the gradient is rise over run. Rise is 4 units from -1 to 3. It's 4 units. Oops. And the run is 1. Okay, so it's 4x, and then the y-intercept is -1. Okay, 4x minus 1. So u steady is 4x minus 1. Okay, all right. So how would we present this? How would we write this out as in our solution properly? Okay, so this is how we can present. Okay, so we'll say let u of xt equals to u steady. So if you don't like u steady, you can write u bar or something. But yeah, I'll just write a few more words for clarity, instead of introducing too much symbols like this. So we'll so you can just write one line. You don't need to formally define it like this. You can just write one line to capture both new definitions, and have this equals to 4x minus 1 plus theta xt. Okay. So that implies that. Okay, good. Okay, so now our target function is changed. So we want to solve for theta of xt first. And what is the domain of validity? Well, the domain is the same because x still so theta captures the difference between, notice over here, right? The theta is the difference between the full solution and the steady state. So that's like theta is like the delta, right? The difference or the fluctuation on top of the steady state solution. But of course, it behaves exactly between 0 and L. So this domain doesn't change. And time doesn't change. Well, it still evolves from 0 to infinity. Okay, how about the PDE? The PDE now changes, right? Because the PDE was single derivative of u steady, well, it's, yeah, u steady minus theta. And on the right is k times, and k is 4 for our question, ddx twice on u steady minus theta. Okay. Now over here, notice this is with respect to time, but u steady here has no time dependence. So this is just plus, sorry. So this is just d theta dt equals to 4. Instead of confusing that 4, let me just keep it as k. I'll plug in the k at the very end of a solution. Let's keep that general for now. Okay, ddx of steady plus that. Now, if you do two derivatives on this, remember this is the u steady, the final state, right? The steady state solution. The steady state solution here, if you do two derivatives, it's going to disappear because this is linear. Okay, so the steady state is always going to be just a linear profile for any heat equation. Yeah, so this is just going to disappear and leaves us with this. Okay, so very interestingly, if you compare with the original PDE for U, this is exactly the same. So by going from U to theta, right? So by going from U to theta, the target function is different, but the domain is the same. And the PDE is the same. Okay, so let's word out. So now we are going to solve for this instead, with this domain and with this PDE. Of course, the PDE is the same, even though we introduced, yeah, we introduced an extra function over here, but because that's linear, it's gonna annihilate by this operator. Okay, but now the beauty is, if we look at the boundary conditions, okay, what would it be? Well, u of x0, so now let's look at the boundary conditions. Let's rewrite, okay, so the boundary conditions. U of x0, okay, so let's put that in. U of x0 is, well, u is equal to this. Let's plug in t equals 0. So when t equals to 0, I have, well, I want to find out what x0 is. So that's identical to u of x0 minus u steady of x, right? Now, this is given to be, by the question, to be 1, okay? So that's the initial temperature profile. That's the initial temperature profile of the rod minus u steady, okay? So minus, okay, u steady, we just copy this, it's minus 1, okay? What do we get? Yeah. Well, x, yeah, that makes more sense. Okay, good. So that's t equals 0. Okay, now let's look at x equals to 0. Okay, theta 0, 0 t. Okay, so again, that's identical to. Let's shrink all this a little bit. Give myself a little bit more space, because this is the key part of the substitution, the change of variable. Okay, so first of all, I'll use the identity sign over here, because this is going to be identical to 0t minus u steady of x. Okay, u steady of 0. Okay, there we go. Okay, so what's 0t? It's given to be minus 1. Okay, minus 1 minus. Okay, let me just quote this so you can match it up each term. Okay, 0 is 4 times 0 minus 1, right? 4 times 0 minus 1. Okay, what do we get? Well, 4 times 0 is 0 minus 1 plus 1, so we get 0. Let's write it over here. Okay, so we get this boundary condition. And how about at L? So at L, or at 1, so we have theta 1t equals to u of 1t minus u steady of 1, x equals to 1, right? So here, what is 1t? Well, it's 3 minus 4 times 1 minus 1. What do you get? Well, 4 times 1 is 4, minus 1 is 3. So again, get 0. Aha, now if I quote these boundary conditions, so this is the boundary condition for t this is the boundary condition for x equals to 0, and this is the boundary condition for x equals to L or x equals to 1. Notice these are now homogeneous boundary conditions, right? So this is the idea that by making this substitution, basically making this change in variable, notice this is the original problem. Target function is u. We went from u to theta. The domain remains the same. The PDE remains exactly the same, which is interesting, right? Of course, it's tailor-made, but yeah. But now, instead of having inhomogeneous boundary conditions for the space-like variable, we now have homogeneous boundary conditions for the space-like variable. Okay, so now you can proceed to solve so now the idea is, right, from here onwards, the strategy is which you continue with your solution is to first solve the theta with all of these boundary conditions, so with all of this PDE, these boundary conditions, this domain, and then transfer it back to and then write it back as u, and then and then get u of x t, right? Because now you know. So that's the strategy. Okay. So maybe in this part 2 of this video, we'll write this out explicitly for you. But before we go to that, you might want to give it a try yourself and see if you can make any progress before we look at the second part of the video.